started. Today is chapter 6, which is the 29th. Wednesday is the finish of chapter 6, and your quiz is a week from today. Chapter 6. These are different distribution and network models. And what's interesting about them is that if you find this interesting, there's a job out there for you. It's called logistics. So search for logistics and learn all about it. It's about scheduling, transportation. Before logistics even existed, one of my first employers way back in the 1980s, a long time ago, we had a logistics person, but we never called her logistics. We said she was our shipping scheduler. And she was worth her weight in gold because she not only made sure our company manufactured plumbing products, plastic and China plumbing products for the bathroom. Tub surrounds, tubs, sinks. And we had our own trucks. So we took pride in shipping directly from the manufacturer to the retailer, kind of telling the small mom and pop do-it-yourself markets that you can compete against Home Depot. Back then it was Andy and Forrest something. You can compete against Lowe's. It didn't exist yet, but because we are going to ship directly to you. And what she was able to do was to make sure all the orders were loaded onto the trucks in order from the way the deliveries would go, so that the front of the truck would be the last delivery and the back of the truck would be the very first delivery. So when they got the schedules in the warehouse to load the trucks, they knew exactly how to load them, bunched together. And where she really paid off for the company is that she was able to network or communicate with all these different companies that are far away from Mansfield, Ohio, where we were located. And she was able to schedule our trucks on their way back to pick things up that needed to get back to Ohio or near Ohio. And that's where she was worth her weight in gold, because so many companies, that was the biggest risk when you buy your own trucks. They head out, you try to schedule them in what's called a half circle, but on the way back there's usually an empty truck, which is just dead money being thrown out the window. So for them to be able to pick something up and bring it and drop it off to charge for that trucking, that fee, is what helped, was like this whole additional revenue that the company didn't have before that. So it's a whole job. It's like a big deal now. It's called logistics. This, when you learn how to use software in the position of logistics, all this scheduling to keep the cost as low as possible, you're using several of these networks. One, for example, you're going to see next week is called shortest route. It's where you're putting in all the stops that the truck has to go to, all the different possibilities, which now can be grabbed right off the map, of the routes that can be taken, and then you write it out as a linear programming model, and it will tell you exactly the route that should be taken that will keep the cost as low as possible. This one here is called a transportation model, which is also logistics. It's all about figuring out what we can supply for this shipping cycle that's coming, maybe the next week, what our customers have put orders in for, which is called the demands, and figuring out the least expensive way to get those demands met from the different locations we can supply those demands from using our trucks. And that's what this one we're about to learn. So you can see fundamentally how this is done. And if you find this interesting, this is a whole career. Good paying, great. Just to get a coordinator's position is a great entry-level position after college because you're getting true business experience, just so you know. So, you ready? You read all this at home, blah, 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 before you got here today. And then, this is an example of what a transportation network, if it were drawn out, looks like. I'm going to try to make this chapter as easy for you as possible by giving you some rules I made for myself, or kind of hints, to make it much easier to analyze this and develop. These are called nodes. On the left here, they're supply nodes. This number on the outside will be how much can be supplied. What I want you to write down, and by the way, these are nodes, but these are demand nodes. Almost, as a matter of fact, every one of these networks, you're learning 5 in the chapter, every one of them, the node represents a constraint. That's the hint. And if you're given a drawing, and I say, hey, how many constraints would be in this linear programming distribution model? You would say how many? I can't hear you. Five. It's no, we got 3 on the demand and 2 on the supply. So 5 nodes means 5 constraints. Now the arcs. These arcs are showing what options are available. Whatever our supply location here is, and however much can be supplied, can deliver to any one of these 3 customers. If any one of these arcs were not here, it represents that that supply cannot deliver to that customer. But what I want you to write down is every arc is a variable. So how many variables are there total in this problem? 6, because you see 6 arcs there. Now, when we get to Wednesday, you're going to see a distribution model called shortest route that I just talked about. That's the only one of the 5 where you've got to be careful because every arc is not a variable in that one. Instead, some arcs are 2 variables because in shortest route they can go both ways possibly. So, but other than shortest route, every arc is a variable. Every node is a constraint. And you're going to see the logic behind how to write these constraints and how to come up with these variables. And it should be very easy if you get the hits and have the rules down. Okay, what else? On the outside here is how many units are being ordered from the customers or what are demand. This is supply, this is demand. Now, here's a little hint. Sometimes the demand from our customers could be more than the available supply. For this to work, you have to add a dummy supply with the number of units to at least meet this. And any units that are scheduled to be delivered by the dummy supply are really trying to tell you who you have to put on backorder. That they're really not going to get their goods, but to keep your costs as low as possible, here's the customer that should be told they're going to be on backorder. They're not getting their goods in this next delivery cycle. Okay, but in a lot of cases you have more supply than what's being demanded. Everything's just normal. It's just when there's not enough supply to meet demand, and you got to have this a little bit here. I told you in other class, I'm not going to try to trick you and make this hard. And even though I was just putting together your in-class assignment for Wednesday, and I realized, you got to have a dummy there, and I don't want to trick you guys and make it hard, so I'm not going to do that. But I want to make sure you are aware of that. You do have to do something like that. Here's our first example. You'll kind of see how this comes along. I want you to visualize this as if you are the Acme concrete company, concrete block company. You're figured out the schedule for this next delivery cycle, whether it be a day or a week. And there's 3 orders in the books ready to go that we have to supply. Let's see, we got 3 orders. Northwood wants 25 tons. Westwood wants 45. Eastwood wants 10. Now, if the question says, hey, draw the network. You identify this, you go, okay, it looks like a transportation network. You'll be able to recognize them as we get going, but what did I just describe? Are these nodes on the left or the right? If I had to draw this network where it says Northwood 25 tons, Westwood 45, Eastwood 10, and these are our customers and these are their orders. Well, that's right, the demand. So how many customers? 3. Putting by 3 nodes right there. And you number the left node starting at 1. You can do this how you want, but it's most common that you start at 1 again when you get to the demand nodes. So I know this is going to be a 1, 2, 3. The reason the numbers are important is when I write, well, let's get to supply. I'm going to make the point here. We have 2 plants that can supply 50 tons. 2 plants, there's the supply, where they can come from. I'm putting 2 nodes on the left. I'm writing this small because I want to make sure everybody can see it without the screen block. And we'll start at 1, put 2. What was this customer? I'm putting N for Northwood. I'm putting W and an E. And this is our plant 1 and plant 2. I got the point, excuse me. Shoot. Passed it. We'll come back. Delivery costs for going from these 2 locations to meet these customers' needs are on the next slide. Here's the deal. If you see no delivery costs in the spot that goes, let's say, from our second plant to Eastwood, or whatever this is called, East something, If there's no number there, that means it's trying to tell you that delivery cannot be made. For whatever reason, too far away or something's up, can't be made. So that's not an option. You wouldn't draw the arc. Okay, look at plant 1. Look at all the customer locations. How many arcs should I draw out of plant 1 to our customers? 1, 2, or 3? 3. If you see there's numbers there from plant 1 to each one of the destinations, meaning that is available to be delivered. Now, on each one of these arcs, I need to put the number of cost for 1 unit, this is in tons, being delivered. So if there's a delivery from plant 1 to Northwood, it's $24 for each ton is our cost. From plant 1 to Westwood is 30. From plant 1 to Eastwood is 40. And then plant 2. How many arcs from plant 2 can be delivered? All 3 also. 1, 2, 3. The number is 30. Uh-oh. You sneezed. More. It's never just 1. All right. Now, the only thing that's missing is you've got to put the amount that could be supplied and the amount that's being demanded. Before I go back to the other slide, do you remember how many tons this first plant could supply? 50. Put it on the outside here. What about plant 2? How many? 50. Also 50. See if you remember this. Northwood ordered how many tons? Is it 25? 40. Is it 45? Someone's 25. What about Westwood? Are they 25?
Westwood's 45.
That's 45? What was the top one?
25.
Wow. Is that you? I like it. What's Eastwood?
10.
Thank you. Okay, okay, I know here. I know the top. Good. All right, you ready? Don't look on if you got the PowerPoint. How many constraints do we have? 5 constraints. Are you ready? The constraints right side is either the amount that can be supplied or the amount in demand. All right? Now, if it's demand, we must meet the customer's request. Right? This is drawn as if we must meet the request. So those constraints are all equal. Not less than equal, not greater than equal, equal. And when if there's more being demanded than we can supply, the dummy node will determine who's not getting it. You still make these equal. The dummy node will be the one delivering, so they'll all be delivered. So these are equal. The supply side, in most cases, you have more supply than what's being requested. And you do not have to deliver everything that's available. So these constraints are almost, not always, but almost always less than equal. Because we don't have to deliver all of them. Even if the left-hand numbers of supply equal the demand, you still use less than equal. Because it'll still work out, it doesn't matter. You should just be in the habit of using less than equal unless there's some extenuating circumstances. Now, every constraint on the left side has the number of variables. Now this is a big trick. I want to make sure you write this one down. Every constraint has the number of variables based on the number of arcs that are touching that node. Everybody hear that? You ready? For example, Northwest is our demand node that we're going to write a constraint for. And the right-hand side would be equals 25. Based on what I said, which is the number of variables on the left side is equal to the number of arcs touching that node that we're writing this for. So how many arcs are touching that node? 2. So there should be only 2 variables on the left for all of these except shortest route. You want to make that clear? When we get to that on Wednesday. I don't want any confusion. So the variables now, we almost always write them as all of them as x, but with 2 numbers to the right of the x. The first one is where is it coming from, and the second one is where is it going to. So on the left side, these 2 arcs, I'm going to follow it. X, 1, 1, plus x, let's see, I'm going here, 2, 1. And those are the 2 variables equal to the amount of the demand, 25. Now here's another hint. The costs are never part of the constraint. And that's the number one mistake that, no matter how much I say this right now, that someone's going to make. I've never had a semester where someone didn't make this mistake. Those costs are never part of the constraints. They're always the objective function. Those costs on the arcs are the objective function, not part of the constraints. Everybody get it? All right, let's get to, you got some of the logic. I want you to help me finish these demand constraints. I'm on node 2. The right side is going to be what? Equal, less than, greater than? Equal to 45, I heard. How many variables will be on this constraint? 2. Help me out. X. 1, 2 plus X. 2, 2. Thank you, George. It sounds like you. I'm not sure though. I heard that direction. Last one. Equal to 10. What are the two variables? X. 1, 3. X. 2, 3. 3 constraints, 3 demands. Now we're going to do our supply. Look at node 1 supply. The right side is going to be what? Less than equal, greater than equal, or equal? Less than equal. Less than equal how much? 50. We're looking at this supply node 1, which can supply up to 50. How many variables will be on the left side? 3, because there's 3 arcs touching that node. That's how you know. And you do not put the costs. You just follow the arcs and use the numbers where it's coming from to where it's going to. The first number is where it's coming from. The second number is always where it's going to. Now we go fast. Ready? x11 plus x12 plus x13 less than equal to 50. I just follow the arcs. x11, x12, x13. So now, obviously, supply node number 2, I probably don't even need to tell you. Right? You tell me. The right side would be what? Less than equal to 50. How many variables on the left side? 3. Help me out, Lang. I'm at x2, 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 all added together. You got it. If you get this logic down, it makes this whole chapter so easy that you only need to study chapter 4 to prepare for it. Because that's where some of you, we're going to separate the A's from the B's. It's chapter 4. You're going to be looking at these problems. You're going to have to write objective functions and constraints and identify the variables. I won't give you a fair warning. And just so you know, I don't want anyone to freak out, emotionally, be emotionally prepared, but there is a seating chart. I'm all about those things. I try every tool. Don't take it personal. I do it for every class. I just try every tool I get my hands on. All right. Now, let's take a look. Do we have it? No, we only have the solution. Here we go. I'm now going to transfer. Oh, almost forgot the objective function. Wow, I almost forgot. Max or min? Oh, big pause. Min. Because what was on these arcs? Cost. How many variables will be in my objective function? 6. How many arcs? 6. You ready? This time, it's every variable with its cost now. This is where you use these costs in the objective function. So I got min, and then I have x. Whoops, I almost forgot. All right? I just got done saying. The first arc has 24 on it, so I'm putting a 24. I'm putting an x, and I'm going to follow the arc, 1, 1. Plus, the next arc has a 30, putting x, and I'm following the arc, 1, 2. Plus, the next arc has a 40 on it. I follow the arc, x, 1, 3. Dot, dot, dot for the other 3. Plus 30, x2, 1. Plus 40, x2, 2. Plus 42, x2, 3. You see the logic? You get the logic down, these 3 that we have right now, these 3 we're learning today, will be so easy to you if you just have those logics down, because that logic's the same for all 3 of them. Now, this spreadsheet's a little different than the spreadsheets we've been using. You're looking now at network model spreadsheets, which has been posted since last week, I think. And again, I highly suggest when you get to the formulas, just use this spreadsheet and tailor it to whatever the problem is. Maybe you don't have 2 plants and 3 customers. Maybe you've got to add a column or add a row. and then you go and look at the formulas. The formulas are here, right down here, and right here. Let me say that again. Right here is the left side, and here's the left side. Here's the 2 supply constraints. Here's the 3 demand constraints. Here's the objective function. That's just like it was in the other one also. So this problem at the top, you organize your data. Notice on the right side, 50-50. On the left side, excuse me, on the right side of the spreadsheet though. At the bottom is over here, 25, 45, 10. And that's where, and here's all your costs. Down here, right here, let me get here. These numbers right here is where Excel is going to put the optimal solution. This will be the amount that should be transported from plant 1 to Northwood. How many tons? From plant 1 to Westwood, from plant 1 to Eastwood. And here's your optimal solution. The amount that should be shipped to Northwood should be equal to 25. There's that constraint for demand. The amount shipping to Westwood, this is adding those 2 together. Look at that right there. Equals sum 21 and 22, I believe. Is that right? However much is being shipped to Westwood has to equal 45. And then over here, those 2 added together, however much is being shipped to Eastwood has to equal 10. Now, the formula here is just adding these 3. However much is being shipped from plant 1, all added together cannot go over 50 tons. That's all it can come from plant 1. This cell is just adding these 3, and it cannot be greater than 50. Now, to help you do solver, I have the page numbers 313, 315. And while you're taking the quiz, if you have a question about Excel, and I'm sure you do on every quiz and the final, that you could go, maybe you open up the spreadsheet or have this printed or something. I would open this up and have it ready to go. You at least can say, oh, I'll go look at 313 to 315 if you can't remember all the things I'm talking about here. So we have the data in there, the cost, the supply amount, the demand. Here's where our optimal solution is going to go. I'm opening up solver. Here we go. Hey, wait, don't look. You got to get those numbers out of there. Hang on. You have a pen that hasn't been filled out. Oh, come on. Whoop, whoop. Now I lost it. Right, here we go. Your solver. Let me get outside. Set objective. Anybody, what am I supposed to put in there? You tell me, or tell me a cell, or tell me what specifically is supposed to go there. Set objective. 16. That's right. Where the objective function is being calculated. This is this right there. What's happening here is this is taking all of this optimal solution and multiplying it by the objective function numbers. You can't see the formula. I'll come back to it. By the way, remind me to come back to that. But max or min? Min. What goes changing variable cells? It happens to be where the answers are going to be, which goes from, what is that, F21, all the way in the bottom right-hand corner. Oh, no. Okay. In the bottom right-hand corner, right there is that H22? So F21 to H22. Okay, now let me get this. See if we can get this fixed so we can see it. Oh, you're kidding. All right. The first constraint, I'm going to hit add. In this case, where's the left-hand side? You start anywhere with these or those. I'm going to start with this one. The left-hand side for the first constraint is right there at I-21, and it's going to be less than equal 50. So less than equal is already in place, and the 50 is in cell K21. Now I'm going to hit add, do another one. Here's I-22, and less than equal is already there, so let me click, come on, right here, and make the right-hand side K22. So as you can can see we got those, both of those two less than equals right there. I'm going to add the other three as one if I can. Let's do that. Add. I'm going to do them all together now, which are these three cells. What is that? F23, G23, and H23 being compared to F25, G25, and H25. Here we go. These three. Oh, come on. Right there. I got to switch this to equals. So I'm doing them all at one time because they're all equal. And then these three cells right here. And that's it. So there's all the constraints. All the three equal together and the two less than. Are we done? Can we hit solve? I see yes and no. What else do I have to do? So that's right. I got to switch this. This right here, is that what someone said? Right here to simplex. Is that it now? What about this? Are we good there? Okay. Is that it now? Can I hit it?
Yep.
This is the minimize? Yeah. Okay. How many are we going to ship from plant 1 to Westwood?
45.
40 tons. 40. Northwood, now what? 5. And then Eastwood from plant 1? 0. How many is being shipped from plant 1 total? 50. How many is going to Eastwood total?
45.
No, Eastwood. 10. Very good. 10. See the totals down here. Notice all the shipments are being met exactly, and we either have slack or slope on the other two constraints, our supply constraints. And is it, first of all, how much is it? Slack or slope of how much? 20 tons. It's constrained from plant 1 or plant 2. So I want to make sure everybody sees it. Plant 2, see it right here? We're shipping 50 from plant 1, only 30 from plant 2. Could have been 50. 20 here. I don't know if I programmed this or what's going on here, but if it is programmed correctly, is it really slack? Yes or no? Is it slack? Yes or no? What is the constraint original less than or greater than equal? What is it? That constraint for plant 2, is it a less than, a greater than, or an equal? Less than. So is that slack or surplus? Wait. Are we recording? Is that recording, John? Okay. Okay, let's do this again. The constraint, is it a less than equal or greater than equal or equal? So is that 20 tons slack or surplus? Slack. I know you're dedicated to that surplus. Anytime the constraint's less than equal, it has to be slack. Anytime the constraint's greater than equal, it has to be surplus. You guys just got to look at the less than or the greater than, and that's the only determination to decide whether it's slack or surplus. And I'm guessing I must have wrote something here that's looking at that symbol maybe. I don't know. Let's take a look at what I put there. I don't remember doing this part. It says if J22, which is that, let's see, here's an if equals less than symbol, then put the word slack. If it's not a less than symbol, leave it blank, it says. But if it's not a less than, don't we want to put surplus? So there's a flaw in that formula.
What if it's equal?
Yeah, what it is. If it is equal, then it would have an error message here because there's nothing. I guess no, it'd just be blank. If the way it's written right now, I'll switch it to equal to confirm that. Because it's either going to say the word slack or be blank, right? So I'll put this in equal and it should turn it blank. Answer that question. What about greater than? It will be blank there. We haven't got an option there. You know, we're still going to be blank. So the only way that will say slack is if it's a less than. So I got a flaw there. So go ahead and fix it when you download this. All right? All right. Now back to the PowerPoint. It's saying that 5 go from plant 1 to Northwood. Is this the same solution we had, by the way? Oh, I almost forgot. I forget. How much will it cost to ship all of our customers' goods for the whole shipment cycle?
$2,000.
That's right. Look where he's looking. The objective function value, we were trying to minimize the cost. That's as low as the cost can get to meet these deliveries. $2,490. And not all these problems have alternative optimal solutions, but there could be. But why waste time looking for an alternative optimal solution? Because it will never get you down lower than $24.90. That's the lowest it can get no matter what solution you find. Go ahead.
Why does it still say slack for plant 1?
For plant 1, because because the way I program that, it's only looking there. It's not determining. It should have a 0. Oh, it is slack 0. Because that's a less than equal. Even though there's no difference between them, it would have been slack because it's a less than equal. But here it tells you there's really none. But you remember on the test, I always said, even if there's none, I want you guys to tell me whether it's still slack or surplus, showing me that you can identify whether it's slack or surplus, even if it's 0. Right? Right? Right. So, there it is, 2490, same answer. We're going now to the next one called assignment. This is an example of what an assignment network looks like, except it's not finished. Look. Not finished. With assignment models, how these are used, like a CPA firm or a law firm or anybody, any organization that has to schedule something that only one can go into. These are called agents, and these are called tasks, but these could be almost anything. For example, one of the questions I think I'm posting as to help you study for the quiz, there's an assignment problem where you're working for a media company, a TV network, and you have to put together the schedule of the lineup for this night, and it has 3 or 4 different time slots, but you've got like 6 different shows to pick. Only one show can go into one time slot. That's a situation where you go with an assignment network because you have 1-to-1. Now there's more shows than we have in time slot, which is fine. This will determine which shows would not be scheduled. The arcs represent what it is that's most important that determines which shows would be scheduled, or whatever the left thing is. Which accountant that works for your firm should be on that project, based on maybe billing hours. You know, like a law firm would go, oh, we can get more billing hours if we assign this lawyer to that project compared to that lawyer, and we'll put together the schedule for you to maximize, as an example of maximization, the billing hours, which means money. And they're greedy like that. All right, you ready? Here's the problem. The only thing missing is 1, 1, 1 would be your supply. 1, 1, 1 would be your demand. It's just a 1-to-1 ratio, and that you need those on the outside.
So those, the 3 there, those would be like the shows.
When you say 3, yeah. This is for 3 accounts are available. Real quick, if there are more tasks than there are agents, this is unsolvable. You have to add a dummy agent. You have to have at least as many tasks as as many agents as you do tasks. You can have more agents than tasks, but you cannot have less on this side. If you'll get an error message. So you got to add a dummy. Again, I'm not going to try to trick you on the quiz and get into the dummy thing, but you need to be aware of it, that's all. Because in real life, we're not this evening. Here's your first example. Let's see what we got here. Jumping right here. Here's an example what an assignment problem will be because, let's say you are the general contractor on several projects. You have to assign the subcontractor. You've got 3 projects tomorrow that need to have subcontractors assigned, and here are the 4 electrical subcontractors you're using on projects. You have to determine which one's not going to get a job tomorrow, because there's only 3 projects and there's 4 of them. So to make the determination, you decide the difference that might save this company money is that because we have a deal of mileage, there's a kind of reimbursement based on how far our subcontractors are from the project. So the amount of miles is the only way to possibly save the company money to get these assigned. When you look at this, I like to ask this question. When you look at this, if you were to quickly make an assignment without doing any math on it, what would be your first assignment? Which subcontractor to which project? Because I always jump to, I'll tell you in a minute. Which one?
What side is?
What side to what?
Universal.
Yeah, this is the first one I look at. I go, well, if the plan here is to try to get the mileage as low as possible. But what's crazy is Universal does not get assigned to C, even though, look at that, how low that is compared to the other numbers. There's obviously a combination of the 3 that will get it lower, even if we don't go after that 14 with Universal. And that's where the math comes in. So let's draw this out before we go on to the next slide. How many nodes will I have on the left? That's right. How many nodes on the right? How many constraints will I have? That's right. Because there's 7 nodes. You ready? Hang on a minute. Maybe I don't have to draw this. How many arcs will there be? That's right. Well, what he did is he looked and said, well, every one of those numbers of the amount of miles are going to have to be an arc of a possibility of a subcontractor being assigned to a project, and there's 12 of the numbers there. Now, I want to give you a hint here. Let's say there's no number right where that 32 is. It's trying to tell you that this subcontractor cannot be assigned to that project, and there shouldn't be an arc here. And if there is an arc, I'm trying to remember here, and I can't remember if you have to use 0. I think you got to put a 0 on it if they're going to put an arc. But I prefer you just leave the arc off. If there's no number here, that's what it's trying to tell you. That, hey, Goliath can't go to that project. You know, for whatever the reason may be. Okay, I'm going to go fast since you guys seem to have this. Here we go. I heard 4 nodes on the left, 3 nodes on the right. Here's what I don't want you to forget. 1, 1, 1, 1, 1, 1, 1. All right? I'm gonna go ahead and number these just like we did in transportation. 1, 2, 3, 4. 1, 2, 3. And what was it? Oh, I want to put some letters on here so I don't forget. This is West Side. This is Federation. This is Goliath. This is Universal. This is Project A. This is Project B. That's Project C. All right. I'm going to West Side subcontractor. Could we assign West Side to any of these projects or only a couple of them? So how many arcs would come out of here?
3.
You got it. Go ahead, Mike, with your question.
What were the ones on the outside for?
Only one subcontractor could be assigned to one job. And the reason I put the ones on the outside is this is what reminds you what every constraint is either equal to or less than equal to. Let me start with the supply constraints. Well, let me get all my arcs on here. Every subcontractor can go to any one of these jobs, so I'm getting 3 arcs to out of each one of them. Now, don't stare at my drawing because there's no way you're going to be able to count the arcs on the, I can tell on the project side. Okay, I'm going to start with node 1 from my agent side. My question for you is, based on the logic, based on the instructions I said, all of these pretty much are like, do you think that this constraint will be less than equal, greater than equal, or equal?
This one would be.
Anyone else? That's not correct. Less than equal, because on the left, which would be like supply if this were transportation, they're always less than equal. Not every one of them have to be assigned, especially if we have more than there's projects. All these constraints have to be less than equal. I'm going to do the first one. Less than equal to 1. That's this one over here. How many arcs do you see coming out of that node? 3. So how many variables on the left? 3. And numbers what? 50, 36, and 16, right? Who said that? You did. No, never put the numbers in the constraints. I'm trying to trick you. I need you. Never put the numbers in the constraints. Where do the numbers go? Objective function only. Let me emphasize that. Don't make that mistake. So here I just got to do the arcs the same way we did transportation. Let's see, there's 3 of them. x11 plus x12 plus x13 less than equal to 1. There's supply, or what we call agent node 1. Help me with node 2. Again, it's less than equal to 1. How many variables on the left? 3. Help me out. X, 21 plus x, 22 plus x, 23. Notice on the supply side, which in this case are agents, the first digit has consistency. 1, 1, 1. 2, 2, 2. The next one would be 3, 3, 3. On the demand side, the second digit has consistency. To show you, I want to go to the first node on the right. This is project A. Less than equal, greater than equal, or equal McCarthy. I mean, I just stunned her. Are you ready? This one right here, help me out. Less than equal, greater than equal, or equal. I'll give you a chance to come back. Equal, because it's the right side, So this is equal to 1. How many arcs are touching that node up at the top? And just try to imagine. 4. So there's 4 variables. I'm going to go x11 plus x21 plus x31 plus x41. It's the demand side or project side, and the second digit has the consistency. 1, 1, 1, 1. The next constraint would be 2, 2, 2, 2 on the right digit, because it's the right side. It makes this real easy. If you guys get these little consistent rules between these networks down, it makes them so easy. All right? Now, I want to warn you. You need to be ready to look at a problem and be able to draw this. And you need to be able to look at a drawing and be able to write these. This goes full circle around. Or maybe even look at these and be able to draw that. The logic is either direction, however it's done, the logic's the same. Transportation, assignment, and transshipment. Slight difference, it's just like the rest of them. All right, so now how do we, this time I'm going to demo, I think, before I say this, I better look. I was going to demo the software. This is an assignment problem, correct? Linear programming, okay. You know I have this already. Let me see here. There it is. All right, here we go. Now look at how it was done in the software. When this software opened up, it said, how many variables do you have? By the way, I forgot to put the cost on each arc, but there should be numbers on each one of these arcs, so this drawing's not done. And the objective function would have every variable with the number. But when it opens up, it's going to say how many variables are there. You just count the arcs. 3, 6, 9, 12. 12. And then it has x 1 through 12. Change it to exactly the way you have your variables. x11, x12, x13, x21, x22, x23, and so on across the top. The variables for the constraints change automatically because you changed them up at the objective function. Now you look at is this the first constraint right here? It only has 3 variables less than equal to 1. You put a 1 underneath the x11, a 1 underneath x12, a 1 under x13, and you leave the other 9 variables blank. See the 3 1s up there at the top of the constraint 1? And all the rest are blank. Let me get all the way over to the right so you can see this. Where is it? Here. All the way across, that's all blank until you got right here less than 1. And that's how you do each of these constraints. What's this one? So on this demand or task constraint, there's 4 variables, 1, 1, 2, 1, 3, 1, 4, 1. So there should be a 1s underneath each one of these variables, and the rest left blank, and then equals 1. So this constraint is this top equals 1 right there. So the third line from the bottom that I'm pointing at. There should be 1s underneath. There's x41, x31. There should be x21. Find the thing to move over. There's x31, and there's x21. And you do that for each of these constraints, just putting the 1s everywhere. The numbers of the cost, in this case, the miles the subcontractor would have to travel, are in the objective function across the top. Now I click Solution, Solve. Are you ready? Who is going to Project C? Who is going to Project C? Subcontractor 1, 2, 3, or 4? I gotta look. I don't say it yet. Hang on, I gotta find it. Oh, I can't find it. Okay, I see it. Do you know how to read this? Look at the 1s in the optimal solution values. Then look at the variables where the 1s exist. Those 1s are telling you which subcontractor is scheduled for which project. The question is, which subcontractor got Project C, which is the 3rd project? Subcontractor 1, 2, or 3, and 4? 1. Because there's a 1 in the optimal solution next to the variable 1, 3. That's this one, 1, 3. There's a 1 there, meaning this is your best assignment. We thought it was going to be subcontractor 4, right? Is that what we said? Subcontractor 4, because that 14 was only $14 cost or something. But instead, 1 got it, which was 16, I think. It was only 2 more. Who's going to Project B, the second project? I got to look.
4.
Yeah, 4. Who's going to Project 1? 2. And who doesn't get a project? Just like 3 doesn't. Because 3, look at 3.1 has a 0, 3.2 has a 0, 3.3 has a 0. 3 has no 1s as an optimal solution, meaning it's not scheduled. Now, I just want to show you one more option for assignment. I'm going to go change models. I'm picking this little shortcut here called assignment. I'm going to find it. It's subcontractors right here. This one's a different one. This is like linear programming, but when you open it up, it says how many agents do you have? And on the left side, we go, oh, there's 4 nodes, so you say 4. Then it will say how many tasks? There's 3. And it opens up a grid 4 by 3 and wants you to put the whatever it is on each line of the arc, the cost or the miles in this case, in the boxes. That's all you got to do is put the numbers there. And if there's no arc, if this subcontractor could not go to that job, you would leave that box blank instead of putting a number in. Then you hit solution. Now tell me again which subcontractor got task B. Whoops. Is this a minute or a minute? So we try to get those miles up or down? Okay. Who gets project B, the second project? 4. So you can see how to read this one. In either case, they both should have said, here's the least amount you can get the miles to with this assignment. What is the lowest we can get these miles? 69 miles. That's right. That's the lowest you can get. I mean, there may be another assignment, possibly. Not all of them have alternative optimal solutions, but even if there is, who cares? We'll never get it lower than 69, so let's run with what is recommended. That's the lowest you can get. The objective function value is the lowest or largest maximum that you can get it. And here's the optimal solution. This may be the only one. There could be more, but it doesn't matter because that's as low or as big as you can get. That's 69 miles. All right, one more. How are we doing? Doing okay. There's our drawing with the arcs on it, just like ours, the meter. Only thing missing here, ones. Ones, ones. Just a quarter point, it's up to you. Here's our constraints. We did this constraint right here, 1, 1, 1, 2, 1, 3. We did the next one, 2, 1, 2, 2, 2, 3. We did this constraint for the project, 1, 1, 2, 1, 3, 1. Notice the ones are consistent on the right, and the numbers are consistent on the left for the supply. And the objective function has all 12 variables with their, their individual costs or miles in this case. Everybody see it? This is too easy, right? Making sure. All right, one more. Here's our assignment. Okay, this looks bad at first, but it's really just as easy as the others. You ready? When would you ever use this, called transshipment? If the story ever somehow is indicating that something, like goods, have to go from a supply to maybe a distribution center or somewhere before it gets to its end location, that's when this model comes into play. In most cases, it's usually a distribution center. You have a big load coming from the suppliers to the distribution center who breaks it up into smaller quantities and then ships out to customers. So here would be any place anything has to go before it gets to the end customers. And this is the supply. Now, the rules or the hints I gave you are the same except for these changes. So transshipment, here's the differences. The difference is you cannot number these 1, 2, and then start at 1 again, and go to 3, and then start at 1, 2 again. Because X11 doesn't make sense. 1, 1 or 1, 1. You have two, you just won't be able to work it out like the other two. So you need to number your nodes from 1 to however many nodes you have. Do not repeat numbers. In this case, 1 through 7. How many constraints will be on this problem? Just right, 7. Thank you. You ready? How many variables do you see? I gotta look myself. Okay, go ahead. How many variables? I heard it up there. Thank you. 12. Just count the arcs. You got the rules. They're the same. Here's our supply. Are these constraints most likely, and you can kind of count on it, less than equal, greater than equal, or equal? Look at your supply, rules for supply. Less than equal. Over here on demand. Thank you. Jumping ahead. These constraints are all, it's just like the other models, equal. Now here's the difference. These middle constraints are always equal to 0. Everybody hear that? It represents whatever comes in heads back out. In fact, whatever comes in is added or subtracted, and whatever heads out is the opposite, either added or subtracted, and that these constraints should always equal 0. It's not going to hold on to goods. It never distributed it out. It has goods come in, and then they head back out after something takes place. And these constraints equal 0. Not less than equal, not greater than equal, equal 0. Period. All right? Now here's the tough one. How many variables would be on this less than equals whatever the supply is for this node? How many variables? 3. There's just 3 arcs touching it. x23 plus x24 plus x25 less than equal to whatever it can supply. How many variables would be in this constraint right here? 3. And the right side, this would be less than equal, greater than? Equal, just catch it. Equal to, the left side would be x37. What did I say here? Did I do 23, 24, 25, or did I mix my numbers up when I said that? Did I? Okay, good. Making sure. x37, x plus x47 plus x57 equals whatever that demand amount is. These are just like transportation, just like assignment. Everything I just said is the same for all 3, right? Now this one, I want to make sure you hear this. How many variables are equal to 0? That's right, 4. 4 arcs. Some coming in, some going out. If you decide to make the ones coming in positive like most people do, then you got to make sure you make the ones going out negative. They have to be the opposite of each other, whichever way you go. If you make them negative coming in, they got to be positive going out. And you have to be consistent with each of the middle nodes. They're all equal to 0. But as soon as you decide if the ones coming in are positive, then the ones coming into every middle node have to be positive. Are you ready? This is what I mean. I'm going to do node 5. Node 5 is equal to 0. We know that. There's 2 arcs coming in, and I'm going to make them positive. I see, help me out, 1, 5, 2, 5? Everyone see that? So I've got x15 plus x25. And now the other arcs have to be the opposite because they're going out. I see x, what is that, 5, 6, and 5, 7? Does that sound right? Minus x, 5, 6, minus x, 5, 7 equals 0. Now, look at node 3. It's almost the exact same. Equals 0, 2 coming in, 2 going out. And you're going to make one set positive, one set negative, but now that you've done one already, you must be consistent with the middle node you've done already. So if the ones coming in are positive on this, the ones coming in on each one of these middle nodes have to be positive. So on node 3 up there, we got x1323, x13 plus x23 minus x. 3 is going to 6 and going to 7, so x36 minus x37 equals 0. I want to make sure you understand, if you decide to make the ones coming in negative, negative x15 minus x25, that's fine. Make the ones going out positive, plus x56 plus x57 equals 0. But when you do these two, you've got to make the ones coming in negative, the ones going out positive, because you have to have consistency, whichever way you decide to do it. Okay? These are almost too easy. Here's the story. We are the middle person. That's who we are. You ready? I'm not going to read it to you. I'm just going to tell you. We provide custom shelving to our customers, but we order in bulk from the suppliers. One supplier is Arnold, and the other one's Super Shelf. We've got this whole thing scheduled where we have 3 customers that need custom shelves. Z, Rock, Hughes and Rockwood. And we have 2 locations that we're going to have these shelves shipped to. And our 2 locations are going to do our thing and then take them to our customers to install them. All right? We're the middle person in this one. We're the ones making the changes, ordering from in bulk, doing some things, and then taking it out to however many customers. So let's draw this real quick. How many nodes do I have on the left? Because, it is 2, because 2 suppliers. Who are they? Arnold and Super Shelf. You got it. So over here, node 1, node 2, this is Arnold, this is Super Shelf. How many can Arnold supply? Says, let me look here. The 2 manufacturers, okay. Arnold and Super Shelf can supply at most 75 units. Putting a 75 right here, putting a 75 right there. Okay, they're shipping them to us. How many nodes should be in the middle? Not 1, we have 2 locations. We're having them shipped to both our north side and south side location. So we have 2 of us. What's the number of these nodes? That's right, you cannot start at 1 again. After we do our thing, we're taking them to the customers because our orders are in at the beginning of the story. How many customers are there? 3 customers. And this is, what numbers do I use? 5, 6, 7. This happens to be Hughes, or no, Steve Rod. This is Hughes, and this is Rockway. On the outside of node 5 should be how many units? Is that what it says? 50? I can't see it. 60, and how many here? 40? All right. Are you ready? Let me keep looking. On the next slide, it's going to show us our costs for getting these from our suppliers to ship to us, and our cost from getting it from us to our customers, but it includes an additional cost for us installing them, I believe, or something we got to do with them. Who cares? Here they are. You ready? Where do I put that number 5 that says Arnold to Xeron North? We're Xeron. That's our north location. Where do I put the 5? First of all, can Arnold deliver to our north location?
Yes.
I'll put an arc there. And then, how much will it cost us per shelf? 5. There goes right on top of the arc. Can Arnold deliver to our southern location? And how much? 7. Can South, I can't remember the name, Super Shelf go to our northern location and our southern location? And what's the numbers here? 7 and 4. Now, can we go from our northern location and possibly deliver to our first customer, Z? We can. And what's the number involved? 1. Can we go from our northern location to our second customer? And what number is involved? 5. And to our third customer? And number? Can our southern location deliver to any one of these customers? That's right, because we see numbers there for all of them. And the numbers are 3, 4, and 4. Is that right? Is this complete, this drawing? It looks complete to me. We have our demand, we have our supplies, we have all the arcs. We're going to do, let's do 1 supply constraint, 1 middle node constraint, and 1 demand. I don't even know if we need to do supply and demand because there's no difference between the supply and demand on this than there is on transportation or assignment. I mean, the same exact rules. On our supply constraints, is this less than equal, greater than equal, or equal? This is your change. Less than equal. These constraints, less than equal, greater than equal, or equal? And these constraints, less than equal, greater than equal, or equal? I mean, you got it. Let's just write this one, node. Let's do node 4 right now. You ready? Node 4, tell me the right side again. Less than, greater than? Equals 0. How many variables will be on the left side for this node 4 in this story? How many variables? Not 2. 4. 4. 2 coming in. No, there's more than 4. You guys have me. 5. 2 coming in. 3 go now. This time, let's make the ones going in negative. Are you ready? Help me out. Negative x coming in. 1, 4. Minus x. 2, 4. Plus x. 4, 5. Plus x. Plus x. 4, 7 equals 0. One's coming in, we made negative. If we now were to do, that was node 4, if we were to do node 3, we have to make sure that the variables going in are negative to stay consistent, and the ones going out positive to stay consistent, equal to 0. The variables for these outside ones are always positive variables. You know, unless you have a special situation. We're only using negatives to show that they're going, some's coming in and some's going out. And the same that comes in has to head back out. That's the only reason why we're using negatives. It's telling the program nothing's left in the center there. It goes to customers or we don't want it. Okay? Let's see. So there is our drawing. Do we have those numbers? 1, 5, 11, 11, 8. Yeah, I guess it's 3, 4, 4, 7, 4. Okay. Our drawing looks like that. Here's the objective function. Every arc with that cost from the arc. So if I go over here, I got 5x13. Is that a 7?
Yeah, it's supposed to be an 8.
Yeah, 1, 4. It's supposed to be an 8 there? 8x14, 7 plus 7x23 plus 4 times x24, plus 1 times x35. You just keep going. The logic behind these are exactly the same for all of them. Here's our constraints. Our supply constraints from our suppliers, less than equal 75 each of them. There were 2 arcs touching each supply node. Here's our center nodes, equal to 0. The ones coming in here are positive. The ones going out negative. Coming in positive, going out negative. Here's our demand nodes, 50, 50, 50. There's 2 arcs going to each one. My question for you is, how many shells are going to our first customer, Xerox, from our northern location? Everybody hear that? How do you interpret that? How many shells are going from our northern location to our Xerox customer? Hang on, I got to look. Northern Xerox. Okay, I see it. How many? 50. That's right. All you got to do is look at the optimal solution based on what the variable represents. Now, when I said from our northern location, that was node 3. To our first customer, Z, node 5. X35's optimal solution is 50, meaning that's what you should be delivering from your northern location to 50. How many are we getting into our northern location from supplier 1, Arnold? What would be the variable on that? X, 1, 3. Go to X1, 3, the optimal solution is 75. This supplier is sending all that can be sent to our northern location. We're obviously delivering, you told me how many, 50 to Z. So node 3 must be, that's our northern location, must be delivering some more somewhere. My question for you is, by looking at that output, where is there additional shells being delivered from our northern location?
6.
No, not 6. Well, 2, 6, yes. 2, 6, but how many?
25.
That's right. All you got to do is look for all the 3s. This is the one we were talking about, 3, 5, but here it is. 0 here, so there's 25, 3, 6. It means, yes, there's an additional, our northern location will be taking additional shells to the second customer, which is Hughes, and it's going to be 25 shells. That's what this output's telling you. You've got to be at the point to where you see this output, and you're going to have a question in words. You're not going to say, hey, look at what the answer is for variable x13. It's going to say, how many is recommended to be delivered from supplier Arnold to our northern location? Then that's how you got to be able to interpret this. You go, oh, that's variable x13, and then look at the optimal solution. How much is going to be, was this a max or a min? Those are probably shipping costs, I'm guessing here, and plus that little extra. We're trying to keep our costs down for our customers as much as possible. What's the least that this could cost us for this whole cycle for our 3 customers to get them the shelves after we do our thing? That's right, 1,115. That's the lowest we can get our cost for our customers. All right. I think I have an example of this on Excel. What do you think? On Excel? No, I think I did this with this. Let's take a look. By the way, switching modules, there is not a transshipment module. You have to use linear programming. Just like the constraints that we wrote and everything. No big deal. Linear programming, I think I have it done already. Transshipment right there. Notice each variable, there's x13, x14, x23, x24, x35, 360, 7, and so on. There's the individual costs that were on every arc. 5, 8, 7, 4, 1. Here are our constraints. Here's our middle constraints. In this case, the ones going into node 3, which is our northern location, are negative. x13 is a negative 1. x23 is a negative 1. And then coming out of 3, x35, x36, and x37 are all positive 1. So in this example, the ones coming in were negative, the ones going out positive. The right side, let me get over here, less than equal to 75, 75. The middle nodes equals 0. Our customers equals 50, equals 60, equals 40. How many did we say we are delivering from our northern location to that first customer? Was it 50? Let's see if the answer is the same here. From our northern location, which was node 3, to our first customer Z, which was node 5, are we delivering 50? And is the cost the same as before? Was it 1,150?
Yeah.
It was. Okay. So, and if you wanted to use, we have it up. This is just me. We got 5 minutes anyway. You're gonna take attendance. Going class today. It'll take you a second. All right. Any questions? We have a quiz this tomorrow, right? No. All right. All right. I'll see you on Wednesday.